15 direct proofs. 1 minute apiece. Good evening, everybody. This is the 7th lecture of discrete math. We're going to do set theory tonight and set proofs. So last time we started with some set definitions. We talked about what a set is. So who remembers what a set is? It's a group of stuff, right? So it's a group of stuff. Does order matter?
No.
Order doesn't matter. And how do we count? We only count each item once, even if it's listed more than once. And how do we write a set? We start with curly braces. And then we write our elements. And then we end with curly braces. And what is this set? That's the empty set. And how's the other way I can write it?
Curly bracket, curly bracket.
2 curly braces. Okay, now I have a pop quiz. Trick question. How many elements are in the set A?
One.
One element. You are so great. Okay. How about the next A? How many elements are in the set A?
2.
One. Okay. The reason why I introduced this example is to show you my suitcase trick. Okay. I think of a set as a bag or suitcase of stuff. So this outside one is a suitcase, and if I ask you how many things are in A, then I start looking inside, but all of the sets inside get closed up like little suitcases. So there's only one suitcase inside A. There's one thing inside A. So the size of A is 1.
Excuse me. For the first one, the size is also 1, or size is
Yes,
either.
the size is 1. It's a different element, right?
0.
This A here, let's call this A1, and this is A2. A1 is the set containing the empty set. A2 is the set containing the empty set. Yes?
If you replace the empty set with like a real element, would that still be just 1?
Yes. So the empty set is a real element. It's just like a container. So that's how I think of the empty set. It's like a container.
And it doesn't matter how many you have in that container.
Right.
The answer is still that it always has one.
That's right. If this suitcase had a million things in it, like it would be if it was my bag, it would still be one item counted inside the set A2.
But we will say A1 has no elements, right?
A1 has one element, and its element is the empty set. So the size of A1
Got everything lined up now.
is equal to 1.
Isn't that sort of saying nothing is equal to 1?
No.
Are you saying A1 is a suitcase with nothing in it?
I think I need to do an example. Okay?
What
I
does
have-
the suitcase represent in A1? It's just
This
you
is a
would draw a
set.
suitcase
Okay?
around.
This is a set. This is a bag. Okay? Can't really see it on there. This is a set. It has some stuff in it. So I would have to count how many things are in here. Okay? I don't really want to show you what's in here, but that's all right. My brush, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 things in it. This is a bag that has something in it.
All right.
I don't count how many things are in it. I just count it as one thing because it's one thing inside here. Okay? Does that make sense? So just because something's empty doesn't mean it doesn't count as something. It counts like Tupperware. You know, if you had a whole bunch of Tupperware inside Tupperware in your cupboards, you wouldn't say your cupboards were empty, would you? Just because it doesn't have food in it doesn't mean that it's nothing. Yes?
So for A2, where you have the outside braces and then the inside braces holding the empty set, could you omit the null symbol and just have 2
No.
pair of braces,
No,
and
you
that still
never
be the
get
empty
to
set?
omit anything. So whenever I see this, I don't think of it as nothing. A lot of times in your classes, you think of it as the empty set, so you think of it as nothing. It's a set with nothing in it.
So if
So it's a set, so it's not nothing.
say for example A3, you had curly bracket. I think this was your question. Curly bracket, close curly bracket, close curly bracket.
This is like, A3 is like a giant suitcase
With just one
with another suitcase inside it that has another suitcase inside it.
But is that a valid notation to have
The
just
suitcase notation?
the 3 sets of curly brackets? Now, I know that suitcase notation is
Of
valid.
course this is a valid notation.
Okay.
Okay, as long as my curly braces match up, that's set notation. This is a set containing a set which contains another set, which happens to have nothing in it.
Now, could A3 have the empty set and a set with something in it?
Sure.
Does you have multiple?
Sure, I could have that, like that. But that's actually the same thing. So let's do some other examples, okay?
So if you wanted like a set A that the size of which was 0, you would just do curly brace,
Right,
with nothing in it.
right.
And then, or you could
So the question was, if I wanted to have a set that had nothing in it, I could put either curly brace, or I can denote it as this.
and that size is 0.
And the size of this is 0. The size of both of these is 0. Okay? Yes?
So what about the first sign has 2, 0 stuff inside? That's two atoms or 1 atom.
On the previous slide?
Yeah, even this one, you put the, you have 2 expressions for the empty set, right?
Yeah, they're
What about
two
you put,
equivalent
2
expressions.
second, expression in the first expression, side by side?
If I put a set that contains both of them,
No, yeah, yes, that's a
the
2
size
atoms.
of this set is 1 because empty set is equal to the empty set, right?
Yeah.
So this set, let's call it D, is really equal to the set containing the empty set, which is a set with 1 element. So the size of B is 1, even though I wrote it twice. So that was a good question.
All right.
Have a question. If you have a set, let's say A4, the A4 include A1, A2, A3. A1, A2, A3, they are all empty sets. How many elements that they got?
If I have a notation like this, I would say that A4 has 3 elements.
But both A1, A2, and A3, they are all empty.
But the elements of the set A4 are sets.
Okay.
So just because they don't have anything in them doesn't mean it doesn't have anything in them. So this is like having 3 suitcases in here. So if you were to start talking about the contents of a bag being empty, suppose that you went to Europe and you knew that you needed a lot of space to bring back all the stuff you were going to buy for your friends, right? So you're allowed to have 2 bags. So in one bag you pack your stuff, okay, and in the other bag you pack like a suitcase and you have a carry-on inside there, and both of them are empty. Do you think that the airport personnel would say that they don't have to put a bag on the plane for you, for that one? They still have to put something on the plane for you, right? It's your bag. So just because it doesn't have anything in it doesn't mean that it's nothing. Okay? It's a container. Think of it as a container. Okay, so the curly braces are like Tupperware or like suitcases. Okay? This is another example of where you just need to let yourself think like a computer. Okay, I treat everything the same. All right, so if I'm looking at a set, you want to know how I really count how many things are in a set? I do the suitcase trick. So if I have a set containing the empty set and the set containing the empty set, I really would think of this as one thing. So I would come to this comma, I would say that's 1 element, and I would come to that comma, see a curly brace, and then I would go to the end of it, and then I would count that as one thing. So even if it had three things in it, I would say that's 1, and then that's 1. So B has 2 elements. It has the empty set, and it has the set containing the empty set A and B. Okay, now we're going to make it slightly more confusing.
So B has 2 elements. So
B has 2 elements.
A has two elements too if you can't look inside.
A has two elements also.
But there's
So
that.
does A. Okay, so we need to be able to tell how many elements a set has. And elements can be the empty set also, or sets containing the empty set. But as soon as I see curly braces, I just don't even count the things on the inside. I go to the end curly brace and I count that as one item that I have to pick up, because someone has conveniently put them all in a bag for me. So I only have to carry two things. It's like if you went to the grocery store, someone asks you how many bags do you have, you don't tell them how many things you bought, you tell them how many bags you have, right? Even though you might have bags inside bags, you wouldn't count those either, right? You would say how many you had to carry. And that's what kind of question we're asking when we ask how many elements are in the set. So there might be containers inside that have things in them, but I want to count how many main items there are. You'll just have to practice. You'll get better, I promise. That's what most of the stuff in this class is like. Just before I move on, though, this is called size of, but it's also called the cardinality of the set. And it's called that because the numbers, like 1, 2, 3, 4, 5, 6, 7, those are cardinal numbers. So if I ask you about the cardinality of a set, I'm asking you how many items are in the set. So that's just a definition that you need to know. So let's do some examples of sets and figure out how many elements are in them. So if I say that A is equal to the set containing elements X so that X is an integer, remember that we used Z to represent integers, and X is less than or equal to 100, and X is greater than or equal to 0. So what is the cardinality of A? 100. Sorry about that.
100.
The cardinality of A is 100 plus 1, because we include 0 also. So if X was bigger than 0, it would be 100. But since it includes 0, then the cardinality of A is 101. So if I wrote that set out, I would write it like this. I would write 0, 1, 2, ... and then I might write 99, 100. Because that tells people the rule for writing out the set. So the dots denote keep writing just like you were, and then you put another comma and show where the end is. Okay, are there questions about that? What does this bar mean?
So that.
So that or such that. So how do I read this?
A is the set of
A is the set containing elements X so that X is a member of the integers, and X is less than or equal to 100, and X is greater than or equal to 0. Okay? So notice throughout this course we've been counting different things. So first we counted how many types of values our variables had, our logic variables. They had, 2 usually. And then if we had multiple variables, we were counting how many combinations there were of them to figure out how many inputs we would have for a circuit, how many possible inputs we'd have. Now we're counting members of a set. So we're going to be counting things all semester. And the reason why we count things is there's lots of reasons in programming, because you want to be able to count your inputs, count how many outputs you should have, generate all your test cases, and there are lots of applications. So you need to be good at counting. And that little trick problem I gave you of including 0 is probably the one that trips people up most in programming problems. So all of your problems will occur at the boundaries. So Counting in between 1 and 100 is no problem, but then I stick the 0 on there and you have to think a little harder. So pay attention to counting problems because they will be very, very important throughout any computer science that you do. Speaking of counting, I'm going to give you another definition right now. Of a power set. A power set of the set S is the set containing all the subsets of S. So why would I want to generate something like a power set?
That's combinations. Anything?
That is a combinations problem. It is. But why would I want to generate such a thing?
Well, if you run a computer, you may want to know all the files and all your subdirectories and stuff like that.
Right. So if I have a system where I've got lots of files, and I might need to count like the total number of files. I'm not sure if that's a really good example. Let me think of another example. A power set might be
Real numbers.
if I'm thinking of a set. So think of you have lots of students. I have lots of students in this class, okay? And I have my computer tutorials, right? I might have any group of you take them on any one day, right? So if I wanted to think of all the possible ways that all of you might or might not take the tutorials, then all of those listings of all the combinations of you taking the tutorials on a day or not, all the possible ones would be in the power set because all the possible subsets of the class would be in there, right? So what's the smallest number of people I could have out of this class?
1, 0.
0, right? So I might have nobody. That's a set, right? The empty set is a subset of any set. Okay, so the empty set's probably going to give you more headaches than any other kind of set. But think of, when you're thinking of the power set and you're thinking about making a power set, let's just talk about a smaller set like A, B, C. When I think about making the power set here, I think about all the ways of either leaving elements in or taking them out. All the possible subsets come from this or taking things out of it, right? So this is the largest possible subset. So the second largest subsets would be, so that's one of them, right? A, B, C is one. Then what would be another possible subset that's almost as large?
2 elements.
2 of the elements. So how many ways are there to get 2 of the elements?
3.
There's 3 because I could take out any one of the 3 elements, right? Okay, so now I can take out 2 elements at a time, right? And how many would there be with 1 element?
3.
Oops, sorry. And then I could take out all 3, right? And there's only one way to do that. So this set with all of these is called the power set of A.
So will it always be 2 to the power of, generally speaking?
Right, the number of elements in the power set is 2 to the number of elements in A. So let's notice this. We have 3 elements, so the size of A is 3. So then, if the power set has 2 to that power, it should have how many elements? So the size of the power set should be 8, so let's check it out. 1, 2, 3, 4, 5, 6, 7, 8. So I'm happy that I made them all. The way that we came up with the 8 was by taking out all the possible ways I could take out elements, right? So I could think of the power set in another way. I could denote it another way, which will help you remember why it's going to be 8, which is 2 cubed. Okay? I'll show you. So what I'm going to do is I'm going to transform this set, ABC, into a string. So the string is going to be this. It's going to have 3 positions. And it's either going to have a 0 if I have an A in the first one. Sorry, a 0 if I don't, and a 1 if I do have an A. A 0 if I don't have a B, and a 1 if I do have a B. And a 0, 1 if I don't have a C or if I do. So all the possible subsets is equal to all the possible strings of 0s and 1s of length 3. Okay, so let's list them. We can start with the smallest one first. We could start with no elements, right? Then I could say, well, I could put B and C in there. I could do it in order of binary counting also, right? Which would make me happier because then I would make sure that I could check and make sure I did all of them and didn't repeat anything. So I could just count.
Where did you get the first numbers from again?
This?
No, those numbers under the A, B, and C. You got 0, 0, 0, 0, and then 0.
These are all the possible strings that are represented here. So in the first position, that tells me whether I have an A or not.
Okay.
It's a 0 if I don't, a 1 if I do. Same thing in the second position for B, and the same thing in the third position for C. So this is a representation of all the possible subsets of the set containing A, B, C.
So is B actually considering A and B? Or
No.
it's just B?
These are separate.
Okay.
Each position is telling me whether A is in the set or not. The first one is telling me whether A is in the set. The second one's telling me whether B is in the set. And the third one's telling me whether C is in the set or not.
Okay.
So this one corresponds, the first one here corresponds to the empty set, right? The second one corresponds to what set? The set containing C. The third one is the set containing B.
BC.
The fourth one is BC. The fifth one is A. The next one is AC. The next is AB. And the last one is the entire set itself. And all of these are subsets of ABC. And the power set contains every single one of them. So when I write the power set, I have to put curly braces, list all of these with commas in between them, and put curly braces at the end. And that's how I write the power set. And this tells me, this is really cool because it's just like we've been doing on truth tables. I can count how many ways there are. And then that reminds me that it's 2 to the power of how many things are in the original set. And this is a really useful thing because then if you have a problem where you may or may not have an input, you can check all the possible types of inputs this way. So you might have been thinking of the problem as a set. This is a nice way to map it into a binary string problem, which is a lot easier to deal with on a computer, right? Computers deal with strings a lot better than they do with, I have a set that has 3 things in it, okay? So let me write you one more definition, one more way to write the definition of power set. So the power set of A is equal to the set of all sets B. I'm using a capital letter because I mean for it to be a B, where B is a subset of A. So the elements of the power set of A are sets, and they're subsets of the original set. So this is the set theoretic definition instead of the English definition of a power set. So remember that this is the subset symbol. If you see a subset symbol like this, it also means subset. Sometimes it means proper subset and sometimes it doesn't. And what I mean by proper subset is smaller than, like not actually equal to. So the difference between these two is just like the difference between less than or equal to or less than, although let me warn you that some people use this to mean this. Some people use subset to mean subset or equal to. But if someone wants to make sure that they really strictly want a subset that's not equal to the set, they'll do this. They'll draw the subset, and they'll put a line underneath, and then they'll put a slash through the line. I'm not going to use those in here, but I wanted you to know what they were in case you do some set theory in some other classes, which you probably will. Are there questions about power sets? So if I saw a set, how could I tell if it was a power set of something or not?
How many curly brackets? If it has curly brackets.
Okay, let me give you an example. Can this be the power set of another set?
Sure.
Yes. No.
Okay.
Well,
If you say yes, then you need to figure out what set it's the power set of, right? If you say no, then you need to tell me why you know. Can it be the power set of something?
Sure.
yes.
It cannot because it has 3 elements. That's not a power of 2. Right? All power sets have powers of 2 numbers of elements. So this has 3 elements, so it cannot be a power set. So let's call this C. The size of C is 3, so therefore C is not a power set. It could be a subset of something else, but a power set is a set containing a bunch of sets that are subsets of the biggest one.
Can you ever have a set of power sets? Or is that just not usually done?
I could have a set of power sets, but in this class we were not going to deal with them because it would be very hairy.
I didn't know if it would be useful or not.
I'm not sure. I'll think about that. I mean, it probably could be useful for some problem, but I'm not sure about that. So if I have another set, let me give you an example that looks a lot more. This looks closer to what might be a power set, right? Because all the elements are sets. So one way I can check is I can count the number of elements. Then I can check that all the elements have to be sets. So here, this problem still is that I only have 3 elements. So if I wanted to complete this to make it a power set, what would I add? The set containing A and B. So that's not a power set, but this is. The empty set, A, B, and the set containing A and B. So the last trick to do if you're trying to tell if something is a power set is to look at the largest set inside your power set, or inside your candidate power set, and see if that set is the power set of the largest one. So the largest one in here is either A or B, and this is absolutely not the power set of one of those, right? So if I look at this one, though, I can double check that it's a power set. The largest element is the set containing A and B, and so then I can generate the power set and check to see that it's equal to this. Has the empty set, has the set containing A, the set containing B, and the set containing A and B.
The 2 sets you have right there are not equivalent, though.
No, they're not equivalent. They're not. They're 2 separate sets. So G is equal to the power set of the set containing A and B.
Of what? I suppose you'll tell us what, now that we know what a power set is, what good it's going to do us. I hate to be redundant, but
Yes, I understand.
we
Like
have no idea where
I just
we're
told
going
you
with
why
this,
you would
so.
want to know about power sets. So if you have things that might be, like if you're working with a program and you might have inputs but you might not, or like say you're working at a door to a dance or something, or some event, and people have signed up and registered, but they may or may not show up. So I have all these different possibilities of people showing up or not. So I have a list of people, I have a set of people. The power set would denote all the possible ways I could have people showing up. Even if they've signed up, they may or may not come. So if you're writing a program, you could test whether your program works by going through, if you have a set of possible inputs, Your power set of your set of possible inputs will tell you all the possible combinations of your inputs. And you'll need to test every single one of those to see if your program works. So that's I know it's kind of an abstract application, but there are other less abstract ones, but I'm in the middle of thinking abstractly right now, so it's a little difficult to come up with something. But when I do, I'll email the class. Okay? I will. Okay, let's do another definition. So we've got sets, we've got definitions of sets, we know how to count how big they are. Just one more thing before we move on. How do I find the power set of this set? It has 2 elements, right? So we should have how many elements in the power set? 4. Right? 2 to the power of how many elements are in the set. So what I do when I do this is I think of this first one as A and this first one as second one as B. Then I generate the power set for AB, which would be the empty set, the set containing A, the set containing B, and the set containing both. And then I'll go and replace all the A's I see with the empty set and all the B's with the set containing the empty set. And then that way I don't mess up how many curly braces I have. So it's doing substitution temporarily. So everywhere I see an A, I put the empty set. Everywhere I see a B, I put the set containing the empty set. So whenever you have a problem that looks sticky, make a substitution, solve the problem, and then resubstitute again. And then you're sure that you've got it right. Because you can double check. This is again B, this is A, this is B, this is A. So every power set problem where your set has 2 elements is going to look similar. Okay. We just need to do one more definition for set theory, basically. So we did combine sets in several ways the other day. We tried union, right? That was all the elements from both sets. Intersection was elements that were in both sets, but not just exclusively. So A union B was this diagram where I take all the elements from A and all the elements from B and combine them in a set. The intersection just takes this middle piece where they overlap. These are called Venn diagrams, if you remember. We had A minus B, which was all the stuff that's in A, but not in B. We had A exclusive or B. Which is the opposite of the intersection, right? If you think of it, if you're just talking about within the union of those 2 sets. We also can think about the universe outside of A. So A complement, that little C up there is A complement, is all the stuff outside of A. So usually people draw like a box to denote the universe. And then the complement is all of the elements outside of A. And we can write that with our set theory definitions, like we've been doing the others. A complement is X so that what?
X is not in A.
X is not an element of A. so those are all of our different ways of combining sets. And your homework's going to have problems where you have to do those combinations. So you're given a set A and a set B, and you'll have to figure out what the union, intersection, difference. This is called the difference also. This is called symmetric difference also in set theory. Exclusive OR is called symmetric difference in set theory. And that can make some sense to you if you look at this picture, sort of the reflection of that picture. And then we have our last new definition for sets there. I'm going to talk to you a little bit about the plane now, just for a minute. So this point here, where I have x, y, how would I write that point?
X and then 1.
I would put
One.
parentheses, and I would put 1, comma 1. Right? So how about this point here?
1, negative 1.
That would be 1, comma negative 1. So in this graph, we're writing x, comma y to denote a point. This is an example of a cross product of two sets. This is a picture of a cross product of two sets. And that's the next thing that we're going to talk about, is the cross product of two sets. So this is the cross product of the real numbers with the real numbers. So this x-axis is the real numbers, which is denoted with a big capital R. And the y-axis is also the real numbers. And the cross product is all of the points where the first element is from x, the x-axis, and the second one is from the y-axis. So before I gave you a definition, I gave you an application for cross product. Okay, so the cross product is the set. So if I have A cross B, that's how I read this, A cross B. That's the set of ordered pairs little a, little b, so that little a is in the big set A and little b is from B. So I can write that in my set notation as the ordered pair AB, so that little a is in big A and little b is in big B. So anytime you have anything that has ordered pairs, you're doing a cross product. So let's do an example of a cross product, a small one. So if A has the points A, B, C, and B has the points 1, 2, 3, first of all, before we do this, how many points do you think is going to be in A cross B? I'll give you a little hint. This little X is like times.
9, that's right.
So there'll be 3 times 3 elements. What's another, we've seen the plane. What's another notation where we're doing something like a cross product?
Yeah. No.
Where you see like a little X like that. I'm thinking of a matrix, right? We have rows by columns. So if we want to denote an element in a matrix, we say row, comma, column. And that tells us which element we're denoting. So there's lots of applications of cross products. So here it's the set containing ordered pairs where the first element's from A, the second element's from B. So I have all the ones that start with A. I write those first. It doesn't matter what order you do them, but I just do it this way so I don't get mixed up. So I know I should have 9 elements because the cross product has the product of the number of elements from both sets in it. So we've actually been doing cross products all semester because we've been talking about logic values where we have, say, two inputs where we had P and Q. And we had P would be 0 or 1 and Q could be 0 or 1. And then we were talking about combinations of P and Q. And order mattered, right? So we could have denoted them as ordered pairs, and then we would have been doing a cross product of all the values of P and all the values of Q. And that's why we had 2 times 2 rows in our truth table, because all the combinations of all the values of P and Q is 2 times 2, because we're doing a cross product of the two possible sets. Questions about that? So again, how many elements does a cross product have? Multiply the cardinality of the original sets, right? Okay, let's see. So if I give you 2 sets, you should be able to look. Sorry. I can give you a point, and you can tell me if it's in the cross product. Is X comma A in A cross B? No, because X comes from B, and A comes from A. So the order matters. Remember, I said ordered pairs, so order matters. So this is not an element of A cross B. It's in B cross A. In this case, what is A cross A? It would have AA, AB, AC, BA, BB, BC, and so on. So I can cross a set with itself. There should be commas all in there. So A cross A is a combination of all the elements from A followed by elements from A. Now, I've told you before that we use predicate calculus and set theory together. So let's try that. Okay? Okay, just in case you didn't get enough examples with people and dogs, let's write some statements. All humans like dogs, and let's see, all humans like dogs or cats. Let's just not leave some people out in here. They like dogs or cats, and let's see. All humans who like cats, give me something that they would also do. Have gardens. I'm just making up a problem. So let's prove that all humans either like dogs or they have gardens. So let's write these in predicate calculus, and then we'll do these in set theory also. So we'll use set theory definitions. So I wanted to do a predicate calculus proof, and then we'll go and do a set theory proof also. And it'll also be in predicate calculus. Okay, so let's say that h of x is that x is human. And I'm just making this up. You can do this yourself. If you get a problem and it's not given what your variables are going to be, you can make up your own variables. Okay. And I'm going to say, let's see, like dogs or cats. I like dogs. Humans like. I'll let d of x be that x likes dogs, and c of x equal x likes cats. And then I'll also say that g of x is that x has a garden. So our first job is to write quantifiers for these, and then we'll have to combine them. Okay, so the first statement says all humans like dogs or cats. So if I'm human, then I like dogs or I like cats. So since I didn't give you a universe for x's, they could be other types of creatures. So I have to say, if I'm human, then I like either dogs or cats. And that's true for all x. Then my second line is all x, if you're human and you like cats, then you have a garden. And then I want to prove if you're human, then you like dogs or you have a garden. So there's several steps. In a problem like this, first I have to come up with my variables, my predicates, and then I have to write my quantified statements, and now I have to do my proof. And the proof is going to be just like the formal proofs we did with logic. So let's try that. I've written so big, I don't know if I have room for reasons, so get another piece of paper. Okay, so these first two are given. I'll just put a G next to them.
What do you call that step when you go from English to the for all x of h?
I'm writing our statements in predicate calculus.
Okay.
So what I need to do is I need to get h of x implies d of x or g of x. So another thing I can do is like go to the side, since all of these are for alls, then all of my rules should work just fine if I rewrite this in something that's easier for me to see what I have to prove. Okay, so then I would go solve this problem and then go write it in predicate calculus. Okay? So let's solve this one and then we'll go back and write it in predicate calculus. Those are my givens. So I haven't figured out what I want to do yet. So I'm just going to make, I want to rearrange this to have C and H separate, I think. I'm not sure. Does anybody have any ideas?
Get rid of the implication first.
Implication.
Get rid of the C.
When you use simplification, get the C by itself and
You know, to
factor
prove.
these.
Then get rid of
I
C.
could use simplification. I could say, what?
C implies G.
C implies G. That's right. Okay, so I could say H and C implies C, right? Or is that what you wanted to do?
I was thinking C implies G.
C implies G.
H and C implies G, therefore.
C
No.
And C implies C is true. Okay. What we'll do, since the most important thing here was actually just converting to the predicate calculus, and then you can do your formal proofs, is we won't do this example because I don't want to waste your time. Okay, because I didn't work this one out. Most of the time I work them. So then I would write them, but I'd have the same reason. So I'd write them here. If I used the implication rule, say for on line 2, I would have for all x and then negate my hypothesis. Change the implication to the or, and or it with G. So if I use the implication rule on line 2, that's what it would look like. Okay, so you can do these proofs because you've done them for your homework. You just need to be able to convert them into predicate calculus and then do them. But just remember that if I have a there exists, if I combine a for all and a there exists, what do I get?
There exists.
I have to get a there exists, right? So be careful. If you have a there exists in a proof, make sure that if you combine two lines, a for all and there exists, you get a there exists at the end. All right, let's do another one that will be easier to prove. So suppose I give you that P is a subset of Q, and Q is a subset of S. I could prove that P is a subset of S. Right? Now, I can't write a proof with set theory notation. I have to use it with predicate calculus notation. So I have to convert these into predicate calculus. So I'm going to let P of X denote X is a member of P, and let Q of X denote X is a member of Q, and let S of X denote that X is a member of S. And then I transform my problem. Now, what is subset with predicate calculus? If P is a subset of Q, then if X is in P, then X is also in Q. And I just use an if-then, so that's implication. Okay, so if I want to convert that, this is P of X for all X. If I'm in P, then I must be in Q, if that's a subset. Same thing for the second one. If I'm in Q of X, then I must be in S of X. So that comes from the definition of subset, because that's what that picture looks like for the first one, is we have Q contains all the P's. So if X is sitting in here, it's also inside Q. Okay, so that's where this definition comes from. So I want to prove for all X, P of X implies S of X. And this is a much more straightforward proof, right? What rule do you use? Hypothetical syllogism. So if I have for all X, P of X implies Q of X, and I have for all X, Q of X implies S of X, then I can use hypothetical syllogism with these two to get for all X what?
P of X implies S of X.
S of X.
P of X implies S of X. So that was from 1 and 2 in hypothetical syllogism. And that's what I wanted to prove. So on your test or something, don't do a proof where you say P is a subset of Q, Q is a subset of S, P is a subset of S by hypothetical syllogism. Because you have to do it in predicate calculus, because your rules are with ands and implies, not with subsets. So therefore, I can write at the bottom, therefore P is a subset of S, because the definition of subset. Okay, so these are all the kinds of problems that are on your next homework, which is immediately after your test, which is going to be next week. Your test is next Wednesday.
I guess. Is
Okay.
it do the day of the test or the day after?
No,
Like the
it'll be
meeting
due the week after. The week after.
Okay.
So sets are not on the first exam.
Right. Sets are not on the first test.
Oh, okay.
So the test is so that you have time to work all those problems, get the homeworks back, review them, make sure that you understand everything, and then you get to take the test. All right, the last thing I'd like to do is just talk about the multiplexer problem on this last homework, because I meant to email you and tell you that we could solve that problem with 3 multiplexers instead of just 2 multiplexers. Remember part C, you had to solve the multiplexer for 4 inputs using 2 input multiplexers. So how did we make a truth table? Sorry, that's not what I wanted. When I had 2 control bits, I made a table that told me what outputs I wanted to get for my 4 input multiplexer. Right? But if you look at part of this table, it looks like a 2 input multiplexer. Right? So I can go ahead and build a 2 input multiplexer and think of it as a black box. I should have labeled this C0 and C1 because I meant for C0 to be the low order bit and C1 to be the high order bit. So this one is C0, and that gives me the first 2. Now, if I look also on the bottom, that looks like a multiplexer problem too, only also with C0. Right? C0 selects between X2 and X3. Make sense? So we'll draw another box that has X2 and X3. And C0 still selects which one. So let's just call this M1 and M2. Now how do I find my final output? How do I know which one of these I want?
Control.
I could use another switch to tell me which one I want. So what's the difference between M1 and M2 in this table?
Howard a bit.
C1.
C1 tells me which one I should pick. C1, if it's 0, I should pick M1, and if C1 is 1, I should pick M2. So I can use another multiplexer to choose between M1 and M2, and use C1 as the control bit, and I get my final M output. So this is another example. We did the adder problem in class. This is another example of a problem where we're using our previous solutions again. And you want to do that a lot. If you've already solved a problem and had someone make the chip for you, you should reuse it whenever it makes sense to do so. So if you didn't have a 4-input multiplexer, you could build it with 3 2-input multiplexers. Probably be a little more expensive than building another AND and OR gate, right? Because how many gates were in the 4-input multiplexer? How many gates
5.
when we originally designed this? So I could think of this as a min-term. If I were designing the multiplexer, that would be C1 is false, C0 is false, and output X0 if those are both true, right? So then that was min-terms. Sorry, I could do C1 false, C0, X1. So my function that I'm outputting M is actually equivalent to that statement. All those min-terms or together. So I would use 1, 2, 3, 4 gates with 3 inputs each, and then an OR gate, so there would be 5 gates. So that would be a lot cheaper actually than this. But if I happen to have a bunch of these laying around, a bunch of multiplexers laying around, then I would want to implement it with multiplexers. So it depends on what you have. how you want to solve the problem. So I want you to be able to solve problems in several different ways so that you can use the resources that you have.
Was that a plus outside in front of the X, CNC? That little symbol you got?
Here?
Yeah.
That's a plus. Those are ORs.
Or together.
Those are all ORed together, yes.
Yeah, say in the test, like in the question you gave that use 2 inputs, 2 multiplexers, and or some OR gates you could use. So how would you do that? No, you didn't say use a third, just use and.
Well, in this case, I would say, well, C1 will select between M1 and M2. So if C1 is false, select M1. And if C1 is true, select M2. So what I would do is I would make, instead of this last multiplexer, I would just use the circuitry that's inside a multiplexer again. Right? So this would be M1, and I would feed C1 negated into an AND gate. And then I would OR that with M2 put into an AND gate with C1 going straight in, and OR those two together. Right, because this is how I do a multiplexer. I use my control bit to select the input that I'm going to output. So if my control bit was low, it selected M1. If it was high, it selected M2. More questions? No, so there's how I would have done that. There's other solutions. This is just probably the simplest solution. Any questions about sets? About using predicate calculus in proofs? Nothing?
Yeah, that's about right. That
Okay.
sounds right.
Let's see, the next thing that we're going to do then, let's just do a little introduction then.
Question.
Yes.
And
I knew you would come
power.
up with one. So, let's do something new. Oh, I have a million questions. Okay, yes. What is that?
Under the power, you wrote the power under power sets P of A, and then the curly brackets B such that B is a subset of A. Would you explain
So-
once?
You want me to go over the definition of a power set again with the notation I used? It's the set containing all the sets so that B, all the sets B so that B is a subset of A. So this notation tells me that the power set is a set whose elements are sets, and they're also subsets of A. So this is so that again. The capital letter usually means that it's a set, and then when I see subset, I'm sure that the B's are sets, and they're all subsets of A. So the power set is the set containing all the subsets of A. So I'll ask you a question then. How many numbers are there? How many integers? Let's say integers. That are divisible by 4. How many integers between 1 and 100?
25.
There are 25 of them, right? So how many of those same, out of the same set, are divisible by 6?
100 divided by 6 is 12, 72, 16, 18.
There are 12 of them, right? Or is it larger than that?
Yeah, it's gonna
12
be
times
more
8
than
is
that.
90,
So it's 6.
like 96.
No, it's 6.
No.
It's not 8.
Sorry, divisible by 6. So 6 times 12, 8. 8's,
18.
I'm sorry, 18.
6 and 12, 72.
So the largest number divisible by 6 less than 100 is?
84.
16.
No.
16. 96.
60, 72, 84, 96. You aren't not helping me. 96 divided by 6 is what?
15.
16.
16.
Yeah.
So there's 16 of them. I'm in front. You guys have to like use your brains to like do calculations. I can't do calculations, so there are people looking at me.
No, it's our fault.
Okay, there's 16 of them. So how many are there divisible by either 4 or 6?
8.
One way to solve the problem is to write down both of the sets of numbers and take the union and count, right? The union is OR, right? So the answer to this problem is a set theory problem. The first set is all the numbers x so that 1 is less than or equal to x is less than or equal to 100, and 4 divides x. That's how I write divides. It's also the same line as the so that line, but I make it a bit longer. Okay? The next one was x so that 1 is less than or equal to x is less than or equal to 100, and 6 divides x. And we said the cardinality of the first set was 25, and the cardinality of the second set was 16. So let's just call the first set A and the second set B.
Shouldn't it be x divides 6?
No. X is divisible by 6. So 6 divides x. 6 is a factor of x. That's how you read this. You read it as divides or is a factor of.
Can we put the backslash and not get in any trouble, because that's not going to work.
You'll get used to it. Okay, so A is numbers like 4, 8, 16, 20, 24, 28, 32, 36, 40. Well, I have to figure out which ones are divisible by 6, right? So I probably want to write them all out.
12.
You have to name them all.
12. You forgot to put 12 in.
4, 8, 12.
I missed 12, sorry. Okay. 56, 60. 4 goes in 60, good. I was just double checking myself that I didn't write any numbers that were wrong. Okay, so there's 25 numbers in A. B should be a lot easier to write. 6, 12, 18, 30, 36.
42, 43, 52, 60, 66, 72, 78, 84, 96.
Okay, so A union B is what?
All of them, but
The reason why I'm doing this problem is so we realize that the size of A union B is not just 25 plus 16, right? Because there's overlap. So if you have to count a set that's a union, you have to add the elements from both, but then you're going to have to take away the ones you added twice. Okay? So let's figure out what they are, the ones that overlap. Let's circle them. 12 is in both of them. 24 is in both of them. 36. 48.
Every 2 at the top.
60, 72, 84, and 96. So there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So the size of the union is 25 plus 16, but then I have to subtract 8 of them because I would have added them here and here, so I have to take them out once. That's called the inclusion-exclusion principle. So how could I have told, without writing them all out, how could I have told how big the set was of things that were divisible by both 4 and 6?
So does it work if you just add them together and then subtract half of the smallest set?
No. Look at the numbers I circled, what's the smallest one? Every single number I circled should be divisible by 12. Because I'm talking about divisibility, right?
Yeah.
So the least common multiple of 4 and 6 is 12, because that's the first number that has 4 and 6 as a factor. And 12 is going to divide all the numbers that both 4 and 6 divide. So the numbers that are divisible by 12 are the numbers that we have to subtract, because that's the intersection of all the numbers that are divisible by 4 and by 6. They're all divisible by 12 if they're divisible by both of those. So the inclusion-exclusion principle is very important in set theory. And in counting, the size of A union B is equal to the size of A plus the size of B minus the size of the intersection. And if you think about that, we'll just look at the picture. It will help convince you that the total size of all of these two circles is the first circle, let's like copy it over again, plus the second circle minus that middle part. Because I added the middle part twice, so I have to take it back out once.
So to figure out the size of the middle, the intersection.
There might be tricks to figuring out the size of the intersection, right? So in that particular problem, knowing that all of the numbers that are divisible by both 4 and 6 will also be divisible by 12, that would help me solve the problem.
So find the least common multiple,
Right.
and count the number of times that occurs.
That's right. So in the two sets that we had, A was the numbers divisible by 4 and B was the numbers divisible by 6. A intersects B was the set of all the numbers so that X, 4 divides X, and 6 divides X. But that's equivalent to the set of X where 12 divides X. So that was something you could figure out. It wasn't something that you should have known before today. It was just an example of where we might need to take out some things. If we add two sets, we're going to have to take out things that we added twice. All right, thank you. I'll see you next time.